Mm-hmm.
Okay, so last time we concluded with the sheaf of divisors and more, let's say maybe the main result from last time was that exact sequences of sheaves are exact if and only if the corresponding sequence of stalks of said sheaves are exact for every point. So this actually lets us prove the exactness of the Ram complex, which we actually have not discussed yet. So we know what is the Ram cohomology, but we've never looked at the Ram complex. So we take a smooth manifold and of dimension n, and then we have the sheaf of sections of this particular bundle is denoted by C infinity p m. So this is the sheaf of smooth sections of the pth external power of the cotangent bundle. So when you take it on an open set, because remember here this is sheaf, so we have to take it on an open set, then this is p forms on that open set. And but we have a special name for its global sections, which is omega p m. So this is the sheaf, I mean, not the sheaf, sorry, the set, the vector space of smooth p forms on M. Okay, the C infinity module, or all the structures you want. And of course we have, from to go from p to p plus 1, we have the differential operator. And we know that, yeah, if we take a point and we take M a star-like neighborhood of X, small x, then this sequence is exact. So here we have 0, here we have, this is the sheaf of constant functions, locally constant functions, sorry. Otherwise it's not a sheaf. And we just immerse it into smooth functions, and then here we start with the differentials. So just take the differential operator, and we know that this is exact. Why do we know that it's exact? Because U is star-like. So we have the Poincare lemma, which tells us that the cohomology of this complex is 0. Right? So the Ram cohomology of U is 0, which means precisely that the image is the same as the kernel of the future map. And the interesting thing is that star-like domains, so star-like neighborhoods of a point, form a neighborhood basis of X. So of a point X, form a neighborhood basis of X. And therefore, when we take the direct limit, in particular, we can take the direct limit over this particular neighborhood basis of star-like domains. So what we achieve is that if just look at the stalks, this is exact. And yeah, by the theorem from last time, we got that the sequence of sheaves is exact. The sequence of sheaves. Okay. So this is one particular exact sequence of sheaves, which is exact. then we'll shortly see that having such a exact sequence of sheaves actually gives us important results in cohomology. But before that, let's look a bit at, so one thing that we did here was to take a bundle, vector bundle, and consider its this sheaf of sections. Okay? So what we're gonna do now is explore a bit the relationship between, again, between a bundle, a vector bundle, and its sheaf of sections. Okay. So this starts a new part called Morphisms and Operations. So in particular, we're going to start with a complex manifold. Can be smooth, but I prefer complex. And we take vector bundles E and F over X, of course. Bundles. And we take cursive E and cursive F, their sheaves of sections, of holomorphic sections. So these are complex holomorphic vector bundles. So the question is now, so a very basic question, we have a morphism of vector bundles. This should somehow induce a morphism of sheaves. I mean, that's what we expect, no? And in fact, we can define phi tilde from cursive E to cursive F. And this will be a morphism not only of C modules, let's say, but OM modules. As the idea is clear, if you do it on a particular open set, then you take a section of the bundle E. Well, we basically act by pullback. So phi composed S F of U. And of course, here S is a section of E over U. Okay. And the lemma is simple, that if phi is injective, phi tilde is injective, and if phi is surjective, then phi tilde is surjective. And remember, surjective, surjective for morphism of sheaves, it's not open set-wise surjective. It's like locally surjective. So let's prove it. Well, the first thing is that it is enough to prove it stalk-wise, which is very nice, because the idea here is that stalks over a point basically represent local sections. So we can basically work in Cn. Yeah. But let's do everything carefully. So assume that phi is injective. And let's assume that over a specific stalk, we have some element which goes to 0. These are morphism of modules. So what we want to prove is this f of x, fx is 0. So this is a stalk, it's an equality in the stalk. So there must be a representative. So there exists a neighborhood of x and an f, which is an honest section over here, such that phi u tilde of f is equal to 0, and say f x equal fx. Remember, I write this thing because in principle, this fx is just some element of the stalk, while here I take f, which is a section, and I take its image under the direct limit. So this is why I put it outside. But of course, you understand why I immediately write f and fx, because we know that this is locally represented by something, which is we'll call f. So what does it mean? What does this mean? Well, that this map, so i.e., the map that takes a point P and maps it to phi composed f of P is the zero section of the bundle F restricted to U, right? So being zero means being the zero section. But now, of course, we can use the fact that phi is injective. So phi is injective, it's a morphism of vector bundle. So in particular, f of P is zero for every P in U. Therefore, the image under the direct limit is also zero. Okay, so nothing too complicated. Now let's look at surjectiveness. And as usual, surjectiveness is a bit harder. Okay, so let's say we're surjective. And as before, now we take an element in a stalk here. And let's take U, trivializing for E and F, and such that there exists a G in FU such that Gx equal Gx. Okay, so we just take this U. Of course, we can take it as small as we want. So we take a U which is small enough such that we have a representative, and it's also small enough to be contained in a trivializing chart for E and F, both of them. There are only two of them, so of course this is possible. So, and now let's simply write phi in local charts. So phi of YV. So we're identifying phi with the phi compose the local charts, yeah? Well, this must be something like y, comma, a, y, of y, times v. And what is a? Well, a is just a function from a into just a set of matrices. And what is the dimension of this matrix? Well, it's rank E times rank F. And as a function, so this is just think of this as a vector space, it's just C to the rank E times rank F. And as such, we want it to be holomorphic. And since it's surjective, the rank of the matrix A of Y, it's equal to the rank of F for all Y in U. Okay. Now in the same chart, so in that same chart, we also want to look at G. So G of Y, it's also going to look, I mean, it's a section of F, the vector bundle F. So this is going to be something like this. Yeah. But now since this has full rank, by the implicit function theorem, the equation A of Y times V equal V of Y has a solution Y goes into V of Y. Yeah, here with the V is the thing we don't know. So think of this as an equation, and we apply the implicit function theorem to this equation. So when you derive with respect to V, what you're left is this A of Y and its maximum rank So we have a solution. And this is true in a neighborhood of this point X that we started with. So now now it's clear we can simply define f of y to be y, y to be y, comma, v of y. And of course, now if we take f tilde of u, so on this particular u where the trivializations are the given ones, we get this. Which of course implies the same equality for the direct limits. Okay. Actually, we have something better, which I will leave as an exercise. That is that if, so we don't only have injective implies ejective and surjective implies surjective, but we also have that exact sequences produce exact sequences. So the process of taking sections of a vector bundle, homomorphic sections of a vector bundle, produces exact sequences. So it's an exact functor. So this is one direction. So we have sections of a bundle, and sections of a bundle are a sheaf, and all the morphisms between the vector bundles translate to morphism of sheaves in a good way, in the sense they respect, for instance, exact sequences. So in particular, as we saw, injectiveness and surjectiveness. So let us look at the inverse situation. So in particular, we take phi tilde from E to F, morphism of locally free OM modules. So we know that if you have a sheaf, which is a locally free OM modules, this must be the sheaf of sections of a vector bundle, of a holomorphic vector bundle. Yeah, we saw this before. Every time you have a locally free OM module, this corresponds to some vector bundle. Okay, so let E and F be the associated holomorphic vector bundles. Okay, and well, from this we kind of want to associate the so we need to define phi, basically. That's what I want to do, right? I need to define the corresponding map, and usually the best way to define a map between vector bundles is to define it fiber-wise. I mean, I give you a fiber, and here I have a linear map. So how do we go from a sheaf to look from a locally free sheaf to the corresponding fiber? And the idea is to mod out everything outside. So let's see what that means. We take mx. So this is not meromorphic functions, but this is a sheaf of ideals. Sorry, not a sheaf of ideal, but just one ideal. The maximal ideal given by germs of functions vanishing on at x. Okay, so this is just all holomorphic function. Then you look at germs of holomorphic functions, and you take precisely the one that vanish at the point x. Yeah? And you know, when we have a module, we can also consider ideal of the ring times the module. So like this. This is a finite dimensional vector space. And why is it finite dimensional? Because this is locally free. So it means that locally is just the product of this OMX. So in particular, when you take the stalk, this is just a product of OMX, and you're dividing by something, and you still have a finite number of generators. And it is a vector space because this is still maximal ideal. So this is a vector space over what? Well, over OMX mod MX, right? But this is nothing but C. Exactly, again, because this is a maximal ideal, so this is a failed. And now if we have a local section here, by the way we constructed this vector bundles, it means that if you take the direct limit, so if you take the corresponding germ, and you evaluate it at a point, this is an element of this, not of the stalk, sorry, but of the fiber, really of the fiber, because that's how we define this. So in particular, this proves that EX is precisely this vector space. Why? Because you just consider the morphism that sends a germ to the germ evaluated at the point. And what is the kernel? Well, it's precisely this one. Yeah. Maybe it's not so clear. So let's have a look. So we send fx to fx of x. So this is clearly surjective because this is all possible local sections. So you can just do whatever you want. And what is the kernel of this map? Let's call it theta. This is ex, and this is ex. And the kernel of theta is, well, precisely mx times ex. Maybe this equality is not clear.
No, I think now it's clear.
Okay. You just need ID component to be 0, so every component must be divisible by something which is 0. So this is why we have this mx.
Hmm?
Okay. Okay, so now it's time to define our phi. I mean, the goal here was just to define this phi. Okay, so we do it, as I said, we do it fiber-wise. So we take an element of the fiber. And the thing is that every element, so this map, as we said, is surjective. So every element of the fiber, it's actually a germ of a section evaluated at the point. So meaning there exists a neighborhood of X and a section over this neighborhood, sorry, E, not F. Which takes precisely this value. If this feels a bit sketchy, just think that, I mean, this is just, everything is local. So you can think that U is just some small, as it's a ball, and in a ball, it's easy because you can always interpolate. And now I think it's pretty obvious how you define it. You just take the image of the section and then evaluate it at the point X. And this is an element of fx. Okay. What maybe is not clear that it's well defined, but it is well defined. Because, for instance, this is OMX linear. So it's also a morphism of, so when you do this, it becomes OMX mod the kernel linear. So C linear, just meaning linear over the fiber. So it's a vector bundle morphism. Vector bundle morphism. Yeah, and also it's OMX linear. So if instead of A, you have lambda times A, then also lambda is an element You can think of it as a germ of a function evaluated at that point. You can bring it outside. And blah, blah, blah. Okay. Now I'm gonna show you the inverse implications. So that if we start with a exact sequence of vector bundles, we get an exact sequence of sheaves, but the opposite is not true. So we start with, I mean, actually, in a sense, it is true. Let's just say, okay, we'll get to that, what I mean by in a sense it is true. But let's just look at injectiveness, let's say. So the corresponding map does not need to be injective. And we will see why, and then you'll understand what I mean by it, that it kind of is true that exact sequences do go to exact sequences. So we define it this way. Okay. So we simply multiply times z. And z, I think the function z, right? And this is just a holomorphic function in C, so everything is fine. And at the level of sheaves, well, this map, which we call times z, is injective. So I'm just going to put a 0 here. The only place where it kind of looks like it's not injective is 0, right? But I mean, again, when we're looking at stocks, you look at the local thing. So it's not like being 0 in a point forces you to be 0 everywhere. Okay. So it still is injective. And of course, the associated vector bundle is just a trivial bundle. So the associated bundle is just C times C. Yeah? We're going to use the Z coordinate here and the V coordinate here. And the map, the associated map, so and this is just Z comma Z times V. Okay, because remember to define what it is on V, you have to like take a section which is the same, and we can just take the constant section which is V, because this is just a trivial bundle, and then take the image of that, and then again take the direct limit. So we simply have Z times V. Which is in fact fiber-wise bundle morphism, right? I mean, this is a bundle morphism, but it's not injective. So, but because phi of 0v is 0, 0, independent of v. So phi 0 is not injective. Okay, it's injective over every other fiber, but not over this fiber. Why? And here I think it's a very, very nice reason why. I think it is very interesting, especially because then it's not just linked to this example, it's just always true. So the idea is that if you try to complete the exact sequence here, yeah, so if you, okay, you have this first map, you have 0, module, module, and then here you put the quotient module and then the 0. So you're trying to complete this exact sequence. So we complete it. This is exact, but, and this is the big one, Q is not locally free. I think that's the really interesting part. Because basically here the stocks are, we remember that for a quotient, the stocks is the quotient of the stocks. So the stock of the quotient is the quotient of the stocks. So you can just see that here, the stocks is always 0 beside at 0 where it is C. Yeah. So it's not locally free. And this is not just this is a much more general fact. So it's always like this. So we take this to be an injective morphism. Of locally free OM modules OM sheaves, sorry. OM sheaf of OM modules. I think at some point we started writing OM modules. We take a point. Then we're not just talking anymore about the map as a whole, but really we have very precise information about what happens over every fiber. And this is true if and only if QX, defined of course as F mod phi tilde E, X is free OMX module. And again, here it's true. So let's look at again with our example how it fits. For Z different than 0, this is just the 0 module, so it is a free OMX module. But for Z equals 0, this turns out to be C. So it's not OMX module. It's a C module, but that's not enough for us. Okay. And this also kind of fits with what I was saying before, is that if this sequence is exact and Q is locally free, yeah, so this is the same as being locally free. So if Q is also locally free, so if all three of them are locally free, then the corresponding sequence is exact. This proposition doesn't prove it yet, but it's a little spoiler. It just proves injectiveness, no? So let's prove this this fact here. So proof. So if Qx is free, we have, so if you remember, this is something we did, I think, already a month ago. Then this sequence, which of course is exact because this is just defined as the quotient, splits. Yeah, this is just a sequence of OMX modules, so sequence of modules over a ring. And we know that if the last, so if this is exact and the last factor is free, then the sequence splits always. So what does it mean? Well, it means we have inverses. And so this is a morphism of sheaves, of course. It's actually not of sheaves, sorry, my bad. A morphism over the, what's it called? Of stalks, so a morphism of rings. Yeah? And, but in particular, it defines, so H tilde defines Hx from Fx to Ex such that Ax composed phi x is identity. So the same thing, but without the tildes. And this, of course, means that if x must be injective. Maybe a small observation is that this H tilde, it's only defined on the stalks. So this Hx that we have here is not, in principle, morphism of vector bundles. It's only a morphism between the fibers. So for every x, we have an hx, but we have no idea that this varies continually or smoothly or holomorphic with respect to x. I think maybe you can prove that, but we don't need it for this proof. And I think that that is relevant. Like, don't do more than what it's asked. But we just need to prove the phi is injective, and we already know that phi is a morphism, right? So we just want to prove it's injective over every fiber, and this is the fact this is the identity just proves it. We don't even need that H is actually a vector bundle morphism. I mean, it is, but we don't even need that. Okay. Okay, so this is one thing. There is, so this is one direction. Yeah, if this is free, then this map is, sorry, if this is injective, wait, what am I doing? So if it's free, then okay, so if this is free, then this is injective. What about the vice versa? Because we said that this is an infinite if. Vice versa, if phi x is injective, then we know that injectivity basically means that some determinant is non-zero. So it's an open condition. In particular, phi y is also injective for y in a neighborhood of x. Okay. But then since they're injective over this thing, this image is a subbundle. Okay, because it has constant rank. Hence, this object here is a vector bundle. Over here. And well, what is this sheaf of sections? Well, it's just the quotient of the sheaf of sections. So in particular, QU is its sheaf of sections. I mean, because Q was defined precisely at this quotient, huh? No. And this proves, I mean, so this is the sheaf of sections of a bundle. In particular, it is locally free. In particular, the stock is free. Okay. Not convinced.
Why was QU locally free? I kind of missed the argument.
Because it's the sheaf of sections of some vector bundles. So if you remember, if we take a vector bundle and we take its sheaf of sections, this is always locally free.
Ah, I didn't remember. Okay.
Yeah, it's the inverse implication. You have that when we prove that every locally free sheaf is the sheaf of section of some bundle, if you remember. I mean, this we used before. The vice versa is true. Actually, we started with the observation that if you have a vector bundle, you take its sheaf of section, this is always locally free. And then we also prove the vice versa. If you have a locally free, then...
All right.
So vector bundles and locally free sheaves are the same category, pretty much.
Good.
Observation. Yeah, the observation is for is regarding. So here we're only talking about injectivity. So what happens to surjectivity? So if you remember in the proof of I mean, not in the proof, but how we define phi once we have phi tilde. We have that this is surjective, and remember surjectiveness of this, it's enough to prove stalkwise surjectiveness. Surjective implies phi surjective. Okay. So if this is surjective, this is surjective stalkwise, right? And basically this is even like a quotient of the stalk pointwise. So we're good. Okay. So now we talked a bit about morphism of sheaves, and of course the previous times we also talked about exact sequences of sheaves. And when you have exact sequences, you're always interested in splitting. Okay. So we have a manifold. We have a sheaf of rings, commutative rings on M, sorry, and F, E, let E, F, G, B, sheaves of R modules on M. So this is true. This is a thing for the whole section. We say that the short exact sequence 0, F, E, G with maps alpha and beta splits if there exists F from E to F of R modules such that F composed alpha is the identity for F. Okay, so natural definition. And we have a lemma, which is similar to the lemma we had for the same thing, but for modules over a ring. So not sheaves as module, but just modules. So, and that is the following are equivalent. So 0, F, E, G. Splits. There exists a G from G to E such that beta composed G is the identity on G. And there exists an isomorphism phi from E to the sum of sheaves F and G such that I think you know where we're going to, so I'm just going to write it a bit small instead of taking a new page. So here we have the identity, with the identity, here we have phi and this commutes. Sorry for writing it a bit small. And but yeah, it's the same that we did for modules. So if you have a short exact sequence, means that you have a map from E to F, which that's what we wanted to do. This is equivalent to have a map from G to E, which that's what we wanted to do. And this is equivalent to say that the middle thing, it's nothing but the sum of the two external thing. And it is so also with respect to the correct morphisms. And if you remember, the proof of this was a bit annoying for modules. But in this case, it's actually 2 lines because we already know it for modules. So recall that we know it for modules. And we know also that exactness for sheaves is equivalent to exactness stalkwise exactness in correct English. And then we're done because the direct limit is an exact functor. Exact functor. So we're done. So you just use little properties. So you take whatever diagram, whatever property you want here. So let's say the last one. And you know that this diagram is true stalkwise, right? I mean, why is it true stalk? I mean, just take this all equivalences and bring them down stalkwise. Yeah. Then they are equivalent because we know it for modules. But we know that being stalkwise, I mean, these are all property of some kind of exactness. So being stalkwise true implies that it was true for the sheaves all along. Maybe for property 1 and 2, this is not so immediate because we're not really talking about exact sequences, but here we really do have exact sequences. So I think this one is clear. This one maybe is a bit more iffy, but don't want to spend too much time on this. So just know that it comes from the properties of direct limits and from the fact that we already know this for modules. And in fact, we also have, so if you're not maybe convinced about this technique of just, oh, okay, we take the limit, we go to the modules, blah, blah, blah. Maybe you can prove that if G is locally R free, then the short exact sequence always free, always splits locally, important. So what does it mean locally? That there exists, let's say there exists U alpha covering of M such that splits. Okay. And I think again, so if you're not super convinced about this, you can work out the details of this one because the proof is really the same. And as a corollary, and this one kind of shows the power of these objects, is that if you have 3 vector bundles, and if you have a short exact sequence between these vector bundles, sorry, not implies, but just this part of the hypothesis, then it always splits. And I think the idea is clear. You look at the corresponding sequence of sheaves. So the sequence induces an exact sequence of locally free R modules. And here R can be, of course, if you're talking about holomorphic vector bundles, it's OM. Otherwise, it's just smooth functions. Sorry, always splits locally. Important, locally. Otherwise, it's not for sure. Yeah, okay. So it locally splits by the exercise. And therefore, the induced maps also locally split. Now you can just go back and forth between the as we said, locally free sheaves and vector bundles. You can just go back and forth. And here, of course, this is not G, but G. Okay.
So just to, I was confused for 1 second. Why we did all this for sheaves and short exact sequences. It is because we have a different type of subjectivity here.
Mm-hmm. I mean, corresponding to what? To not doing it, or?
What was that?
I mean, you said why did we do it for sheaves?
Yeah.
First of
Why
all,
did we?
I mean, we didn't define, for instance, splitting for sheaves, right? Yet. You can say, oh,
Yes.
okay, but you could have just said it and that's it. Maybe.
No, but why isn't it just the question was more or less if we did it for modules and we know that they are modules of the sheaf, then why do we have to do that for sheaves as well? The splitting lemma. But
I mean, first of all, we didn't define, let's say, so the splitting lemma, you mean this, no?
yes, exactly.
I mean, we didn't define what it means split for modules, sorry, for sheaves, right?
Mm-hmm.
We only defined it for exact sequences, short exact sequences of modules.
Yes,
And
that
well, I
already
mean,
is
once
a
you
big
define it,
difference.
you have to. In practice, no, because if you look at the proof, it's really 2 lines, right? So it's not. But the main, I mean, the thing that which really makes it not such a big difference is the fact that the exactness for sheaves is the same as stalkwise exactness. And then stalkwise we know because they're modules. But why? So I mean, you say, oh, is this because surjectivity is weird in sheaves? In a sense, yes, because if you remember, why is exactness stalkwise equivalent to exactness for the sheaf? Well, it's only because exactness stalkwise does not guarantee surjectiveness for every open set, right? But it only guarantees local surjectiveness. But this local surjectiveness is actually what we call surjectiveness for sheaves. So in a sense, yes.
Okay.
Right. So
Good.
you can say that we define surjectiveness for sheaves in this way. Exactly. So then this taking direct limit is an exact functor. Like.
Yeah. Okay.
So if it's true stalkwise for every stalk, then it's true for the sheaf. Right. But I mean, this seems like, if I explain it this way, it seems highly non-natural. It's like, okay, so then you're just cheating. You're just calling surjective a thing which is not surjective. But if you remember, when we introduced it, it was a bit more natural. The idea was just that if you take the image open set wise, this is not a sheaf.
Yeah.
This is just a pre-sheaf. And then we associate a sheaf to it because we have a theorem which tells us that every time we have a pre-sheaf, we can associate a sheaf. So let's just take that as our image sheaf. Because remember, the sheaf, it's still a functor, right? So a priori surjectiveness doesn't mean anything. We can give it the meaning we want in principle. And in a sense, we give it the meaning we want in the correct category. So we don't take, as an image of a sheaf, we don't take the open-wise image, we just take the associated sheaf to the open-wise image. Okay, which then gives all these notions.
Yep. Okay.
But as you saw, yeah, the proof, I mean, you can say it's the same. In this case, we actually use the previous proof. So in a sense, yeah, it's not.
No, but now I know what to watch out for, so to say, when trying to just pull things over from modules. Okay. Great.
Okay. Let's look at an example, and that is again, one of those minefield things. So even if G, so in the exact sequence as F, E, G, this is R free, we might have that the sequence does not split. So of course, if you're free, you're locally free, so it locally splits by what we said. But what I'm saying is that even if you were globally free in the first place, it doesn't mean that you also split globally. Okay. So let's see this example. So we take just 0, F, E, G, G exact of line bundles. So now we're taking really line bundles over a complex manifold. Okay. And then we remember that if you have such a sequence and you multiply it times another line bundle, this stays exact. So let's multiply by the inverse of G, multiplying the Picard group. And here I'm just going to put directly the trivial bundle. So this is exact as well. And now the claim is that, okay, so of course, this is as most free as it can be, right? Just the trivial bundle. So if the last one splits, so when I say splits now, I mean globally. So does the original one. Yeah. Because this multiplication is all factorial. So if this one splits, then also this one splits. And okay, so basically what we're saying is that every short exact sequence of line bundle splits. We don't know that that's not true, but we will see it. Yeah. So we will see that not all exact sequences of line bundles split. So this is a half example because it's using something we don't know yet. So let's say another example, we would need an example of a exact sequence of line bundles over a complex manifold which is not split. Okay, so this we never saw before, but I can promise you it's true. Okay. So when we were talking about modules, one thing that we had to see was how can we do things with modules. So if you have two modules, you can take the sum of the modules. If you have two modules, we take the tensor product of the modules. If you can take the hom functor, blah, blah, blah. So guess what? We're doing the same thing for sheaves. So we will always have an underlying sheaf of commutative rings with unity. And we'll just give a few definitions. So if you have two sheaves of our modules on X topological space, so remember, I mean, sheaves now we always use them on manifolds, but in principle, it can just be on a topological space. The direct sum, so F plus over R G is just U goes to the sum. Okay, this simple, and the stalk is precisely the sum of the stalks. Okay. W2. And also, if we have an exact sequences of sheaves, then if you sum something to it, that's still exact. Yeah. With this another module. Okay, so this is one of them. Let's look at the hum functor. So in principle, you would like to do something like this. So we want to define this thing, right? As a sheaf. So we apply to U, and of course you expect this to be hum are restricted to U. So define the pre-sheaf this way, and careful, because I'm not taking R of U and F of U and G of U, but I'm taking R restricted to U, F restricted to U, and G restricted to U. So this is a pre-sheaf. With restriction maps. Or U, F, U, G, U goes to R, V, F, V, G, V. And here we have phi W. So each element here is a collection, right? Where W is an open set containing U. And you just take the same, just that you have a smaller collection of open sets. Okay. And yes, I was saying before, so observation, R, U, F, U, G, U does not work. Because we don't have restriction maps. Yeah, this is not going to work because we don't have restriction maps. Okay. So as we said, a priori, this object is only pre-sheaf, but it actually is a sheaf. Okay. So we have to prove the two properties. So proof. Let's take an open set and an open cover of U. Let's take phi, an element here, such that the restriction of U to Uj is 0 for Oj. So we have to prove that phi is 0, no? So what does it mean that a morphism is 0? Well, we take a section here. Yeah. then what this means is that if you restrict from V to V intersected uj of phi V of S, this is 0 for every j. Okay, this is what it means, just this. Just you take any section on a smaller set, and that one is 0. That is the 0 morphism. Yeah. So phi V of S is just 0. But now we can use the fact that G is a sheaf. So if this is 0 on every restriction, then this is 0. Yeah. But V was arbitrary. Then phi is just 0. Okay, so the first point is done, S1. Now we have to go for S2. So if you have things which are the same locally, then you can glue them to a bigger section. So we take a collection, phi j, and each one of them lives in its own little ring. But we assume that they match on intersections. For every I and j. Okay. So we need to define the gluing. So we have to take an open subset and a section of V. So we have to find phi V of S, right? But this S is defined, yeah, on this V, our open set, but we only have local data. So let's just write Sj to be the corresponding local data of S. So the restriction from V to V intersected Uj of S. Yeah. And now simply apply phi locally. This is an element of Uj intersected V. So this is a section of G over Uj intersected V. Okay. And of course, since this is true, they coincide, they match on V intersected Ui intersected Uj. So we have this collection, it depends on J, but if you look at them pairwise, they do restrict to the same thing. In particular, they glue. And of course, this Uj intersected V is a covering of V. To a section of GV. And well, we just call this section the image. Okay, so in particular, they do glue. Okay. So also this home functor is a bit weird. But as everything weird we have with sheaves, it works very well with direct limits. So we have here, we have a standard morphism given by the direct limit. So R F G of U into Rx Fx Gx. So we take a phi. So this is already over set U, and we just take its limit. And remember, actually, an element here, it's phi v, where v is every set contained in U. So we can take the direct limit over the Retic system, which is of open sets contained in U. And of course, once we have such map, since U it's arbitrary, we can also take the direct limit here. Yeah. So we have the stalk of these sheaves have a morphism into this object, which is just homomorphism of Rx module. So in particular, Rx module itself. And you would like something nice about this map, right? For instance, that it's an isomorphism. And in general, this is neither injective nor surjective. So sorry, I lied when I said that everything works well under direct limits. But we do have some properties. So not all is lost. So the so if you consider R as a module over itself, this should clearly, if this were just rings, this would be the second factor, right? This still is the second factor. Okay. We also have, okay, I'm gonna start skipping the R here. We also have that the sum, the homomorphism from the sum, the same of sum of homomorphisms. And the same is true for the other factor. What else? We have left exactness. So this is exact. This is also exact. And also if this is exact, and of course E here is just another sheaf of R modules. Then remember that if you put it on the left, it's covariant. If you put it on the right, it's contravariant. So this is the contravariant version. This is exact. We do have done some special trick with locally free sheaves. So if E is locally free, then the functor hom E dot, so this first one is exact. So it's not just left exact, but it's actually exact. Yeah. And one more. 0 F G H 0. exact and H locally free. Then hom is again an exact functor. But this time the contravariant one. Okay. And yeah, so this is just a list of nice properties of this hom functor, which of course are related and are provable using the same properties that we saw for modules. Okay. Because again, exactness is the same as it. I mean, now it's maybe it's a bit, but here you maybe you have to be a bit more careful because in principle you want to say, oh, like this is true if it's true for the stocks, and the stocks are the modules, so it's true. Careful, because this is not an isomorphism, right? So saying, oh, well, I just go to the stocks, and then for the stocks, this is just a morphism of Rx modules. Well, no. So a bit more careful, but it is all obtainable with the results for modules. I will not do that. One more definition. When we define F tensor G, this is not FU tensor or UGU, but it's the sheaf associated to that. Associated to that. So associated to the pre-sheaf, the intuitive pre-sheaf. So let me give you an example. Let's say that we have a regular complex submanifold of a complex manifold. So M is the complex manifold, S is the regular complex submanifold. And we know that we do such a thing, we can associate its sheaf of ideals. Yeah. And let us also define OS by definition OM mod IS. Okay. And I mean, I'm calling it OS because this is really isomorphic actually to the, I mean, if you just think of S as a complex manifold by itself, this is actually isomorphic to just the sheaf of holomorphic functions on S. Yeah. And now if we take F, is the sheaf of holomorphic sections of some bundle. Which of course we call F. Then F tensor over OM OS is the OS module of holomorphic sections of F restricted to S. Okay, so this is just an example of this tensor product. And we will not do the proof. Not simple. So it's not something you should just see. Okay, this is just a fact I'm telling you. And You can get an idea of why this should be the case, but no worries. I mean, we will not see that. Sorry about this. Okay, so let's continue with just a few definitions. So this today was a lot of definitions, which we'll then put to use next time. So let's take just a continuous map between manifolds, and let's take a sheaf on X. Then we define F star, lower star, F is a sheaf on Y such that F star F of U is nothing but F over F inverse of U. Okay. And it is called direct image on the sheaf. Okay, so just a definition, and just another one. So if you have again a continuous map, and now you have a sheaf on Y, we define a pre-sheaf on X. Given by, you take U and you send it to the direct limit of G of V. But I have to tell you, when I give you direct limit, I have to give you corresponding directed system. So where are these V coming from? So the limit is taken over all V's, which are big V, which are part of the topology in Y, so open sets in Y, which contain the image of U. Okay. So this is just a pre-sheaf, and the associated sheaf phi inverse of G is the pre-image sheaf. Okay, it's just objects. And I'll just give a quick example, which is actually relevant, because we know how to define the restriction of a sheaf on an open set, but we don't know how to restrict the sheaf to submanifolds, for instance. So let's just take a point and take T, the map, just the constant map, change everything to said point. Okay. And now the sheaf locally constant functions. So just something we already saw. You can just think about it as the inverse, the pre-image sheaf of N, where N is the sheaf on the manifold made with just one point, given by N of P equal. Okay, so I'm just saying that you can think of the sheaf of locally constant functions with integer values. On X, you can simply think about it as the pre-image of the constant sheaf on a point. Okay. And particularly if F, so this is maybe a separate thing, if S is a sheaf of R modules, then we can guess that the preimage sheaf is a sheaf of inverse image of R modules. So just some random facts. And now the one that perhaps is the most useful to us, if you have an immersion, we define the restriction f restricted to x as the inverse image E sheaf associated to f. Okay, I'm saying, so this is perhaps the most interesting to us because we knew how to restrict sheaves to open subset, as I was saying before. So it's intersection of open subset, it's an open subset, but we didn't know how to restrict sheaves to submanifolds. And now we know. So today, yeah, was basically just a review of everything we did for modules already, with perhaps just there is a few differences. For instance, the sum functor, one should really be careful about this thing here, which then makes everything a bit harder because you cannot directly use the result for modules. You have to be a bit careful. And also perhaps knowing that the tensor product of sheaf is not trivially a sheaf. You have to take the sheaf associated to the trivial idea. And then you would just have a few examples, in particular, this definition, the restriction of a sheaves to a submanifold. Okay, so this concludes the lesson for today, and I'll see you next time.